Hello, my name is Hyung, and I'm with the Dankook University in South Korea. In this presentation, I'll talking about one of our latest works on 3D gaze estimation from a full face image. When we're trying to solve the gaze estimation problem, the approach of separating the eyes from the face is very common and shows promising performance. However, this approach requires a method to separate the eyes, which incurs overhead in both training and inference. And it also eliminates information from other parts of the face, such as head pose. Thus, we aim at estimating the gaze directly from the image that contains the entire face and trying to solve this problem end to end. And of course, there are many more difficulties with this approach. Since the face is used as input, the model is influenced by the individual's characteristics. Unfortunately, existing datasets contains insufficient number of subjects for generalization. In addition, the eye is an organ that occupies a very small size in the human face, which makes the problem more difficult. And finally, environmental conditions such as background and illuminations affects on the feature. The vision transformer, as known as VIT, showed the significant improvements on performance and the generalizability that surpassed existing CNN models. So naturally, there have been many attempts to apply transformers in various fields of vision, and we also expected that this structure could help solve the preceding problems in gaze estimation. For example, we may be able to deal with the relatively small eye region problem because self-attention is not a local operation. However, the introduction of transformer causes another challenges. First, the computational cost of NLP embedding and self-attention of VIT are too heavy. Second, VIT splits the image into patches to make embeddings. And we judge that this process is not suitable for gaze estimation as it carries the risk of cutting eye into pieces. To solve these problems, we propose a novel structure named CADS. In this architecture, we want to use the global context fusion ability of self-attention. So we project the local feature of the input through a convolution layer to modeling local context and downsize the input before self-attention. This is the approach to reduce computation and improve the performance of self-attention that many VAT variants take. However, what is unique about our structure is that we restore the attention feature map back to the resolution of the input. Through this process, we have the advantage of using the global context fusion of the self-attention without paying every computational cost that occurs by high resolution. Self-attention applies attention to the spatial direction, so we add different attention mechanisms in the channel direction to the reconstructed feature map. The SE, squeeze and excitation, which is most widely used among these methods, is employed. This figure shows the overview of our framework. The model is divided into 3 stages, and each stage contains a specific number of CADs. Such structure is very common in vision models. We just replace the traditional convolution layer with CADs. To verify the performance of the proposed method, we conducted experiments with 4 well-known datasets in gaze estimation. In this slide, we show the performance of the method using CNN, transformer, and ours. Category A denotes that the methods are CNN-based model, and B denotes that they are transform-based. The gaze TR, pure in category B, has the same structure with VIT. Next, we conduct an ablation study to validate our design choices. We remove the convolution or deconvolution layer from the CADs, and the respective results are listed in the table. When we remove the convolution, We used the NLP embedding as a substitute and got worse results. As an alternative to deconvolution, the modified self-attention that reduces computational cost with the downsized key and values is chosen. However, the deconvolution outperforms it. We performed cross-dataset evaluation with a well-known CNN architecture, ResNet, to investigate the generalizability of the proposed method. The table shows the average angular error of the models when trained on IDF or GATE 360 and evaluated on others. The left values are the performance of the ResNet 50, and the right values are ours. As we expected, general performance is increased on never-seen subjects. And finally, this figure shows the visualization results of ground truth and our model's prediction. As you see, the model seems to work well at various head scales and gaze angles. It's end of our presentation. And if you have any question, feel free to contact any of the others. It will be very appreciated. Thank you for listening.